Okay, so last time we started the chapter on coupled harmonic oscillator, right? So we consider this situation, which is slightly different from what you have learned before, right? So because this time I have two masses, right? So connected to the same spring, right? So the harmonic oscillator that you have learned before is kind of just one end of the spring is connected to the mass, and the other end is just fixed to a wall, right? So and today I want to start by an exercise problem. So I want you to spend a couple minutes on an exercise problem, which is very, very much similar to what I talked to you about last time. The slight difference here is that instead of having two particles having the same mass, okay, so here I have this M1 and M2. So that is, I allow them to have different masses. Okay, so but the task I want you to do is exactly the same as what we had last time. Okay, so to find out the equation of motion, and in particular, I want you to find out the frequency of oscillation of this system. Right. So last time we still remember that like this one, right? So if you just consider stretching the spring, right? So on both sides like this, right? So if you do it like this, and then after you release the system, right? So this mass will move to the right, and then the other one will move to the left, and then they will just always moving or oscillating out of phase, right? So on and on. Okay. So here, right? So the difference is that I have the two different masses. Okay. So I decompose the problem into three parts, right? So first, set up the equation of motion, right? So consider the force, right, due to the spring. Or you can, of course, use the method of Lagrangian, okay, so to work on this. Okay. So maybe just 1 or 2 minutes for part A. Okay, so last time we have already seen the special case where the two masses are the same, right? So the Lagrangian given here. And this time you know that all you need to do is to replace this 2m, right? So by m1 and m2 respectively, and then we are done, right? So, and that means the equation of motion here becomes m1, and here becomes m2, right? So that's all you need to do. Okay, so and then now let me just, okay, so let me just write everything on this page. So now we have two differential equations and two variables, right? So x1 and x2. Okay. So and then now it would be nice that if we can kind of just have the differential equations in one variable only. Okay. So then we know how to solve it. So part B. So what I'm going to ask you to do is to consider again the center of mass of the system, right? So and because right, so again this system is isolated, so that I assume that there's no any external force acting on it. Okay, so that means that the center of mass of this whole system is either at rest or moving at a uniform velocity. Okay, and now let's say it is at rest, right? So and even if it is not at rest, even if it is moving in a uniform velocity, right? So you know that you can choose a coordinate system that is moving with it, right? So that from your viewpoint, right? So the whole system is the center of mass of the system is at rest, right? Okay, so and now if the center of mass of system is at rest, so that means that the displacement, okay, so of the two particles have to satisfy a certain relation, okay. So in this problem, I'm going to first, right, so before it is stretched, let's say before it is stretched, let me say that the center of mass is somewhere over here. Okay, of course, it depends on whether M1 is greater than M2 or M2 is greater than M1. But let's say, just imagine that M1 is slightly bigger, then that's why you can see that this green point is a little bit to the left. Okay. So and I will also just so just choose this point as the kind of the origin of the coordinate system, right? So and let me call this length to be L1 and this length to be L2, right? So then the center of mass, right? So the center of mass is at this point, right? And we know that by using the formula for the center of mass, this is given by the following. M1 minus L1 plus M2 times L2 divided by M1 plus M2. Okay. So, and in fact, this is at 0. Okay, because the way that I picked the coordinate system, so as I said, I have already picked this point as at the origin of the coordinate, right? So that's why this XCM itself is by definition is 0, right? So this I have this M1 minus L1, right? So because this is to the negative side, right? So that's why I have this minus L1, right? And then this M2 times L2, right? So this is to this side, right? So this M2 times L2. Okay, so now suppose it is set in motion already, right? So that is after some time, right? So this one goes here and the other one goes here. So then in this situation, okay, so what is the expression for this center of mass, right? So that is after some time, the center of mass is again so this is the origin of the coordinate system, right? So again, M1 times the distance. What distance? So it's this distance, right? So this distance over here is minus L1 minus X1. Okay. So this minus L1 minus X1 over here. Okay. and then the other one. So this part over here, right? So for the M2, so it's M2 times L2 plus X2. So again, divide the whole thing by M1 plus M2. Okay. So, and now I can just rewrite it as this M1 minus L1 plus M2 times L2. Okay, and then minus M1 X1 plus M2 X2. Okay, divided by M1 plus M2. Okay. So, but because I know that this one plus this one has to be 0. So as I told you already, right? So that is to say, right? So this term is 0. Okay. So, but as I told you already, right? So the center of mass position itself is not changing over time, right? So this whole thing is still 0, right? So that is to say, the last two terms added together has also been 0, right? So that's why you have this. Okay. Okay. So now I have this relation over here. Let me just erase, and let me just open a new page. No space. Then I can substitute this M1 X1, the relation between M1 X1 and M2 X2 to this equation over here. And then what you can see is that if I just take the second equation of motion, right, and then I can eliminate, I can express this x1 in terms of x2 as well, right? So then this equation of motion can be written as like this. So now you can see that I have an equation of motion that depends on one of the variables only. So then this one we know how to solve, right? So let me just take one more steps. Like this, right? So, and now this is the second order of derivative equals to minus something times the variable itself, right? So that is, you know that this whole thing, okay, is the omega squared. Right. And therefore, right, so omega is given by k times 1 divided by m1 plus 1 divided by m2. Okay. Like this. Okay. So if you go back to the special case, right, so where we have this m1 equals m2, right, so then what you have is the same as the example over here, right? So you have this 2k divided by m. And actually, one interesting thing here is that you might still remember the concept of the reduced mass that we have mentioned in the last chapter, right? So in the last chapter, I have the two body problem, right? So the reduced mass of the system is defined as the following, right? So one over the reduced mass equals to 1 over m1 plus 1 over m2. So that is, you could also express this omega as square root of k divided by mu. Okay, reduce mass. Okay, so now this is one way to solve it, and this is the same way as what we did last time, which is we set up the two equations of motion. We'll try to eliminate one of the variables. Okay, so but this is not the main method that we'll be focusing on in this chapter. Okay, so instead, what we are going to do is the following. Okay, so these two are the equation of motion that we just obtained, right? So, and what we are going to do is to write this system of equation in the matrix form. Okay, so you can see how these two equation is converted into this matrix vector product. Okay, over here. And now we are going to make use of the knowledge that we have learned in the last semester. Okay, is to make use of the diagonalization. Okay, so of matrix. Okay. So before I move on, let me just go through again one more time on the diagonalization of a matrix. Okay, so just to refresh your mind here. So I have a matrix. Let's say I have this matrix over here. Okay. So what I'm going to do is to write this matrix. Okay, so let me call this matrix A, right? And what I'm trying to do is that I want to express this A matrix as a product of three matrices. Okay, that is, let me write it as this T times this D times T inverse. Okay, so this is my purpose here. Okay, so and actually just to be consistent, let me not call this T, because I think last semester I called this not T but P. Okay, I'll just call this P, D, P inverse. Okay, so P, D, P inverse. Okay, so that I have this matrix, I want to write it as a product of three matrices. Okay, so this P, D, and P inverse. And this D is a diagonal matrix. Okay, it's a diagonal matrix. So, and the way to do it, as you might still have the memory, is that we are going to use find the eigenvalues and eigenvectors of this matrix. Okay, so how do we find the eigenvalue? Right, so the eigenvalue is that we consider this determinant, right? So 2 minus lambda minus 1 minus 1, 2 minus lambda, this determinant, right? And lambda would be the solution of this equation, right? So let me just expand the determinant, right? So if I expand the determinant, what I got is 2 minus lambda squared, okay, minus 1. And this whole thing equals 0. Okay. And that is to say, right, so this 2 minus lambda is equals to plus or minus 1. And that means lambda is equals to 3 or 1. Okay. And then for each eigenvalue, also I can find the corresponding eigenvector, right? So for lambda equals 3, right? So let me consider them one by one, right? So lambda equals 3. I want to find the eigenvector. So what do I do? So I consider this matrix over here, right? So 2 minus 3 minus 1. So minus 1, 2, minus 3. Right, so this is the system I have. And then this is this after Gaussian elimination, right? So you have this 1, 1, 0, 0, 0. Right. So, and now that you can conclude that the eigenvector, right? So for this eigenvalue, right? So would be the non-trivial solution of this x1 plus x2 equals 0. Right? And that is to say, eigenvector is 1 minus 1. Or it can be 2 minus 2, right? 3 minus 3. Right. So and if you want to normalize it, right? So what you have is you make a prefactor 1 divided by square root of 2 in front, right? Okay, similarly, right? So for the other eigenvalue, lambda is equals 1. So my system becomes 2 minus 1 minus 1 minus 1, 2 minus 1. And that would be 1 minus 1, 0, 0, 0, 0. Right. So after doing the Gaussian elimination. And this time, right? So that means x1 minus x2 has to be equal to 0. Right. So then therefore the eigenvector corresponding to lambda is equal 1 is given by 1, 1. Right. So eigenvalues and eigenvectors are found, right? So and then what is the next step, right? So here, what we have is the following, right? So the first eigenvectors, right? So give me this system. Right. And then the second eigenvalues and eigenvector, right? So give me this. Right. So these are the two things that we obtain. So now if we put these two equations together, okay. So what we have is that, right? So on the left hand side, I have still have this 2 minus 1 minus 1 2, right? And then the second matrix, what I'm going to do is that the first column of the second matrix is taken from this first eigenvector. Okay. And then the second column of the second matrix taken from this column vector. Like this. Okay. And then what do we have on the right hand side? So the right hand side, what we have is that we will again have this same matrix here. Right. So because I still have this 1 minus 1 over here. Right. So and also I have this 1, 1 over here. What about the 3 and 1? So the 3 and 1 is written as another matrix. Okay, 3 written here, 1 written here, like this. Okay. So that means, okay, so now let me just call this, right? So let me just call this matrix P, right? So that means that this is also P, and this matrix is a diagonal matrix, which I call D. And this one, the original one, is the matrix A, right? So that is you have this AP equals PD. That is finally, this matrix A is equals to P times PD P inverse. Right. So that's our original purpose, right? So I said I want to write the matrix in this form over here. Okay, so now if I just go back to my physics problem here, right? So why do we want to write the matrix as a product of the 3 matrices? Okay. So it is because now, if this matrix is a diagonal matrix, okay, this is not, but if this matrix is a diagonal matrix, then we immediately know how to solve this system of equations, right? So that is, if I have another system that looks like this, right? So if I have a system looks like this, right? So then that means, so this system, if I don't write it as a matrix form, right? So if I write them out again, so what you have is this one. Right? So ignore everything in black, right? So just look at this. We know how to solve immediately, right? Because the first one is just the equation for U1 only, right? The second one is just the equation of U2 only. You can solve them out separately, right? So then the question is, what is the connection between this system and this system, right? So that is to say, if we somehow can transform or make a coordinate, make a variable change, or I call it the coordinate transformation, such that this system can be rewritten as this system, right? So then we will be able to solve it and then do the inverse variable change to get back to our original x1 and x2. Right. Okay, so then the procedure is exactly relying on the process of diagonalization of the matrix, which we just did. Okay. So in this chapter here, I put some of the slides, okay, so from physics 2051, so the chapter on finding eigenvalues and eigenvectors. So all these slides, okay, so have appeared in that chapter, so in 2051. So this is something that you have exactly seen before, right? So over here, let me go through it once again, right? So this is the system that we are trying to solve, right? So as I said, written like this. Okay, so this is a non-diagonal matrix. Okay. So now, if we be able to do the diagonalization, right? So that means that this matrix is written as, right, so P diagonal matrix P inverse. Right, so this is what we just did, the example. Okay. So now, if we just put this form, right, so back to your systems of equation of motion, this is what we have, right? So in the first step over here, right, just replacing this one with these three matrices. Okay. And then the next step is that I am putting this P to the left-hand side. Right. So that is I'm putting this P to the left-hand side like this. Right. So P inverse, second derivative of the variables, equals to this. And this P inverse and this derivative, the order can be reversed. Okay, because P inverse, well, in a sense, this is just a constant, right? So it's a matrix, but the elements in this matrix are all just a constant, right? So that's why this P inverse can be put after the derivative sign. Okay, so this is the new system that I obtained. Okay, so now pay attention to what I have on the left, right? So I have the second order derivative of this whole thing, P inverse multiplied by this x1, x2. And then on the right-hand side, I have this diagonal matrix. And then I also have this P inverse x1, x2. Right. So then now you can see that. Right, so this whole thing appears on both sides of the equation. And then I'm going to call this whole thing as a new set of variables, u1, u2. Okay. Right. So this P inverse, no matter what, this is a constant matrix. So after you do this P inverse multiplying with this x1, x2, you will just get another column vector anyway, right? So that's why I'm allowed to write this P inverse x1, x2 as this u1, u2, a new column vector. So therefore, my entire system now is written in this form, the form that I wanted. Okay, so because now this system of equation is just with this diagonal matrix, right? And as I mentioned already, if I take this system in matrix form and write it back to the system form, right? So just write them separately. Okay. So there's one thing here I'm going to assume is that I'm going to assume that this lambda1 and lambda2 are positive numbers. Okay, so which in our case are always true. Okay, so because lambda1 and lambda2 are always positive, so I'm just going to let lambda1 to be omega1 square and lambda2 is equal to omega2 square. Okay, and as I will explain later, right, so this omega1 typo here, omega1 and omega2 are called the eigenfrequency of the system. Okay. So this one and this one are something that we know how to solve, right? So is that you know that the solutions are written like this, right? So as we learned in the previous semester. So of course, this is using this complex exponential function. Okay, so sometimes we use the sine cosine, right? So in the last chapter, we actually use sine cosine more than just write this complex exponential function, right? So that is, let me write over here, is that usually we might also write this u1 as a1 cosine omega1t plus A2 sine omega 1t, right? Something like that. And U2 is equals to B1 cosine omega 1t, omega 2t plus B2 sine omega 2t, right? So it, as you like, right? So you can either write in this form or in this form. Okay. So but one thing to remind ourselves again is that we know that at the end we are looking for this displacement of the particles, right? So no matter what we have at the end have to be real numbers. Okay. So and actually one more thing, let me make one more remark here. This A1 cosine omega 1t plus A2 sine omega t can also be written as A cosine omega 1t plus phi 1. And this one can also be written as B cosine omega 2t plus phi 2. Okay. So this red expression is equivalent to this blue expression. Okay. So if you don't remember why, just remember the following formula, right? So you remember the cosine x plus y is equals to cosine x cosine y minus sine x sine y, right? So then if you try to expand this one, right, so you could actually see the relation between this A and phi 1 and this A1 and A2. Okay. Right. So you either write it in this form or this form or this form. Okay, so they are all equivalent. Okay, of course, what are being different would be all these coefficients, all these constants, right? So all these constants will have to be determined by the initial conditions of our systems. Okay, as I will talk about them. Okay, anyway, now let me just take these two forms, okay, for now. And now we have obtained the general solution for this U1 and U2. Okay, so now, but at the end, what we want is X1 and X2, where X1 and X2 are the actual displacement of the two particles that we are looking for, right? So then because of this U1, U2 is equals to P inverse X1, X2, right? So then that means, right, so this X1, X2 is just equals to P U1, U2. Right? You just need to take the matrix, okay, so multiply it with the U1, U2, then you can get back to this X1, X2. And remember this P matrix, right? So it's just constructed by the two eigenvectors of the matrix. Okay, so that means, right, so I can write this system as this, right? So here, this whole thing is my U1. Okay, so and then U1 goes with the first eigenvector, and then plus U2, right? So these terms goes with the second eigenvector. Okay. So and if I want to write it using this trigonometric function, then the solution is written like this. Okay. So now you can see that X1 is a sum of these two oscillating functions, right? So the first oscillating function of this sine cosine function, right? So has this frequency omega 1. Okay. And then the second oscillation function has another oscillation frequency, which is omega 2. Okay. So then that means this x1 is equals to some constant, right? So times omega with this oscillation with omega 1, and then plus another constant, right, times this oscillation function, omega 2. So it would be a superposition of the two oscillations, okay, so with different frequency. So of course this is still just the math. Okay, so I'll then apply, okay, so this to the actual coupled oscillator problem. Okay. So let me go back to the problem that we were talking about, which is this one, right? So follow the recipe, right? So now I'm going to try to find the eigenvalues and eigenvectors. Okay, so for this matrix, okay, so I'm not going to repeat all the calculation procedures slowly again, but all in this slide, right? So take the determinant equals 0 and find the value of lambda. Okay. So this is actually a special case that I'll talk a little bit more. Is that here you can see that one of the eigenvalues is actually 0. Okay, so another is non-zero. Okay, so but we'll go to that. I'll talk about how to deal with this 0. But anyway, so two eigenvalues again, right? So try to find the corresponding eigenvectors. For lambda equals 0, okay. So, okay, for this one first, for lambda equals non-zero, I'm going to just put this lambda back to the system and then find the non-trivial solution, right? So you'll be able to find that this eigenvector can be written like this, okay. M2 minus M1. And then you can see that I have this prefactor over here, 1 divided by M1 plus M2. But you already understand that the prefactor itself, right? So it doesn't change the fact that this is an eigenvector, right? So that is to say, I can totally drop this prefactor, right? So I can totally drop this prefactor and say that this is an eigenvector, right? So, or I can pick any other prefactor to still say that this is an eigenvector. Okay, so here I put this prefactor. Okay, so just to remark here is that I put this prefactor here just to make the eigenvector itself to be unitless. Okay, so I just found this a bit more convenient. Okay, so otherwise your eigenvector will contain the unit of mass. Okay, but that's still okay, right? So because at the end of the day, you do have an arbitrary constant, right? So in front of coming with your solution, right? So and that arbitrary constant will make sure that you have the correct unit anyway. Okay. So but regardless, so this is my choice. So this is the eigenvectors corresponding to this eigenvalue. And what about the other? So the other is the lambda equals 0. So for the lambda equals 0, the eigenvector would be 1, 1. Okay. So now, one thing to say is that if I have this lambda equals 0, will I still have this sine cosine solution? Right. So because if lambda equals 0, that means omega equals 0. Right. So that means I have this cosine 0. Okay. So that's one thing to be careful about, right? So is that if you have the eigenvalue to be 0, the solution, okay, so will be not sine cosine anymore. Okay. The solution instead will be, in this case, again, I put this in the appendix, is that right, so one is non-zero, the other is 0. So that if you go back to take a look at the equation of motions themselves, right? So then this is what you have, right? So that is for one of them. The second order derivative is just 0. Okay. So in this case, the solution is just this linear function in time, right? So instead of this sine, cosine. So therefore, right, so if that's the case, your general solution would be, right, so this eigenvector come with this cosine function plus, right, so the other eigenvector comes with this constant, this linear function in time. Okay. Okay, so now let's plug this back to the physical system. Right, so I have this eigenvectors, eigenvalues, and then the general solution. Right, so as I said, is written like this. Okay, so and here, right, so just to be convenient, I'm just considering the special case where m1 equals m2. Okay, so that's why you don't see m1, m2 here. You just see 1 and -1 here. So now, right, so it's a superposition of two terms, right? So the physical picture, okay, for the first term is the following. Okay, so here you can see that this x1 is a cosine, right? So and this x2 is minus a cosine, right? So that means that both of them are doing this sinusoidal oscillation, but they are exactly out of phase, right? So and this is the picture, right? So I've already explained this picture previously, right? So this one moved to right, this one moved to left, and then when it moved back to the left, the other one moved to the right, right? So then this is the oscillation of the two particles. So what about the pictures for the second term, right? So for the second term, so I have this linear function in time, and then both of them have the same 1 and 1, right? So that means this is talking about both particles, right? So are moving exactly the same way, right? So with this linear time function, right? So that is the picture would be looking something like this, right? So both of them travel together, right? So and this is exactly the uniform velocity motion of the entire system, right? So and at the end, of course, what is exactly going on with the system, right? So we'll have to depends on the initial condition, right? So you can see that at this A, at this phi, at this C, at this D, right? So you need to give me some initial condition, and then I will then I can tell you what is actually going on with the system, right? So for example, right? So if initially the system, the center of mass of the system is not moving at any uniform velocity, then, right, so as time goes on, right, so it won't suddenly start moving, right, so unless you give some external force, right? So if for that case, right, so you'll be able to just drop this term over here, right, and just consider this term, right? And then also you might ask, okay, so what about this A? So how do you determine this A, right? So it really depends on, right? So initially how much you are stretching the springs, right? So that would determine the A, right? So let's say. And also, what about this phi, right? So it would depend on whether initially you are stretching them or whether initially you are compressing them, right? So that would give me a different value for the phase. Okay, so now I think it's a good time to take a break here. Okay, so here we are still considering one spring. Okay, and what happens next is that we are going to consider multiple springs. Okay, so that would be the point where we really talk about the so-called coupled oscillators. Okay, so here in some sense you still just have one oscillating element, right? So which is the spring. So and after the break we'll start with the two springs, three springs. Okay. Okay, so we'll start again at 12:35. First of all, notice that there's one typo I made here for the sign of this x1. Okay, it should be minus L1 plus x1. Okay, so this should be a plus. So this one over here should be a plus, and then this one should be a plus. Okay. So let me clarify one more time because I believe some of you are still not entirely clear about the how to really think of the distance and the displacement. Okay, so for these two masses. Okay, so let me repeat that one more time. So I always consider, right, so going to the right hand side to be positive. Okay, so going to the right hand side to be positive, right? So let me just label it here. So to this side is the side of positive direction. Okay, first of all, right? So, and that is to say, this x2 will be positive, right? So if what I have, if you are seeing what I have in this picture, right? So remember, okay, x1 and x2 are referring to displacements. Okay, so displacement itself, okay, so can be both positive and negative, right? So for example, right, so if I look at this m2, right, so going from this point, right, so if it is moved to this point, so x2 is a positive number. Okay, so now if your m2 instead is going to this side, okay, so if m2 is going to this side, so then I will say that here x2 would be a negative, some negative number, right? So the x2 of this mass will be some negative number, right? So but the displacement is still called x2 anyway. So similarly for this m1, right? So if m1 is to this side, m1 is to this side, then x1 positive number, no problem. Okay. So now if m1 is to this side, right, so to the left side, then the displacement, I will still call this the x1, but this is a negative number. Okay, so then you can see, but you might ask, so why I have this minus x1 here? So the minus x1, okay, so let me write down here. So minus x1 means the distance from equilibrium. So minus x1 in this case, not the displacement, but it's the distance. Okay, so the distance from the equilibrium. Okay. So, but why do we care about the distance? Right, so it's because when we want to know whether the spring is stretched or compressed, right? So what we would need, right? So would be the distance. Okay, so between the two particles. So for example, right? So again, in this case, right? So if I want to find the total length of this, right? So how much it is stretched, right? So I would have to tell you that this is stretched by this much on this side and this much on this side, right? So that's why I want to know this distance and also this distance. So be very careful about the distance and the displacement. Okay, so but if we use, okay, so if we use the Lagrangian, so last time I mentioned the Lagrangian, right? So things will get a bit more convenient. Okay, so you should still remember last time I have a slide for the Lagrangian. Right, so over here, right? So instead of considering the force, right? So when you talk about the force, right? So you want to really be clear about the springs is whether it's stretching or compressed. But when you just start with the potential energy, right? So you will always just start with this term. So -1/2 K something square, right? And that something can be either compression or extension or stretching, right? So it's 1/2 K, right? So it's either compressed right? So in either cases, right? So you have this 1/2 K times this amount, right? So that is either compressed or stretched from the equilibrium position, right? So in either case, they have the same sign, right? So don't have the plus or minus in front. Okay. So one thing to remember, okay, so because okay, so the oscillators, the real couple oscillators problems comes now. Okay, so and we'll have to again use the Lagrangian. Okay, so here we go. Is that this is the system that we are going to consider. Okay, so you can see how it is constructed, right? So I have again two masses, and then I still have the spring in the middle, but now I have two more springs. Okay, one on the left, the other on the right. Okay, so the leftmost and the rightmost, I have two fixed walls. Okay. So and then suppose I just set this up, and then they are all just sitting at equilibrium, and then none of the springs are stretched or compressed, let's say. Okay. So now I'm going to consider, right? So this mass is displaced to the left by some amount x1, and then the other mass displaced to the right by another amount x2. Okay. So I want to study the oscillations of this system. Okay. So you could see that, right? So again, right? So the two of the masses will affect each other, right? So because if it, for example, if the left mass moved a bit more to the right, right? So and then it will change this length, and it will change the force acted to the other mass. And also, right, so each mass is connected to their own springs also, right? So if it is more to the right, then the restoring force over here will be more, right? Trying to drag it back to the left, right? And this one, right? So if it go to right more, then this spring will be compressed more. Also try to push it to the left. Right? So you can see that it's a rather complicated problems here, right? So we do have three. How many forces actually? So if you want to think about force, this one is under two forces, right? So the one on the left, the one on the right, and this one is also under two forces, one on here, the other on here. So, but you, of course, you understand that the force acted on this by the middle spring and the force acted on this by the middle springs form an action and reaction pair. Okay, so but here let's start with the Lagrangian of the system. Okay, so this is the important one. Okay, so again, kinetic energy, potential energy. Right, so the kinetic part don't have much problem with this. Right, so the kinetic energy for the this particle given here, kinetic energy for the other particle given here. So now we look at the three terms for the potential energy. Okay. First term, 1/2 k x1 square, referring to the potential energy of the spring on the left. Okay. Again, the nice thing is that it doesn't matter whether this mass has go to this side or the other side. Right. So if this mass is going to the other side, right? So then your x1 will be a negative number, but that doesn't matter, right? So because I have this k x1 squared. So similarly, now if I consider the spring on the right, right? So this time, from this picture, you can see that this one is compressed, right? So that's why the amount that is getting compressed is this x2, right? So and that's why this is 1/2 k x2 squared. Again, you don't need to worry about getting another expression if this mass is to the right, to the left, right? So if this mass is somewhere here, so then your x2 will be negative this time, and in that case, the spring is extended, is stretched instead of compressed. But still, again, no matter whether x2 is positive or negative, potential energy like this, right? Because of the square term. So finally, the potential energy of the spring in the middle, right? So in this particular picture, again, you can see that this spring is kind of stretched a little bit because this x2 is greater than x1, right? So then the amount that is being stretched is x2 minus x1, right? So and that's why I have this 1/2 k 1 to x2 minus x1 squared. Again, you don't have to worry about what about the other cases, right? So what if this x2 is smaller than x1, right? So and in that case, again, this one may become a negative number, but again, doesn't matter because of the square term. So now I have the Lagrangian ready, right? So once it is ready, then the following procedure is just standard, right? So apply the Lagrange equation of motion, right? So now I have the two coordinates, right? x1 and x2, right? So then the two equations of motion, right? So nothing to be explained here. Okay, so you can see these two equations of motion. Okay, right. So of course, right. So for your practice, right. So you could think of how to use forces, right. So to arrive at the same two equations. right? So that actually not difficult also, right? So this minus kx1 obviously is this force, right? And this k12 x2 minus x1 is this force, right? So similarly, right? So you know how the other one works. Okay. Okay. So now, right? What we need to do is to solve this set of differential equations, right? So same strategy, write it as matrix form. Okay, a matrix form like this. And then what's next? Right. So eigenvalues, eigenvectors. So eigenvalues. Skipping the details, you should be able to find that these are the two eigenvalues. Okay. And remember, this lambda can be written as the omega square, right? So that's why this omega 1 is the square root of this, omega 2 is the square root of this, right? So because it will later you'll find that the solution is cosine omega 1 t cosine omega 2 t. Right? So this omega 1 and omega 2 are called the eigen frequencies, right? So whenever you see problems in coupled oscillators, you hear the terms eigen frequencies. Okay. So there are two frequencies exist in this system, as I'll explain more. But these are the two numbers. Okay. So now, for each eigenfrequency, right? So I can find the corresponding eigenvector, right? So for this one, the omega 1, you will be able to find that the eigenvector is 1 and minus 1. Okay. So one thing also, so you really want to try to just work this out once by yourself, because in the last semester, right? So when we deal with the eigenvalues, eigenvector of the matrix, we just have the real numbers. But here they are all just symbols. So just do your practice one time, right? So to make sure that you obtain this value and this value. So anyway, so the first eigen vectors over here, right? So corresponding to this eigenvalue, and then the second one, right? So you have another eigenvector. This is 1, 1. Okay. So 1 minus 1 and 1, 1. Okay. Okay. So then I have the eigen frequency, eigenvalues, eigenvectors. Then I can just immediately write down the general solutions, right? So now you can see that, right? So as I told you already, so I have the two oscillation terms with different eigen frequency. So let's look at the physical meaning one more time. Okay, so this one, the first one, would be very similar to what I have already talked about over here, right? Is that the two masses oscillate out of phase, right? So again, because of this 1 minus 1 here, this is the out of phase oscillation again. Right? But of course, now I do have the two more springs, right? So on the side, right? So when it's doing the out of phase oscillation, which I also call it the so-called anti-symmetric mode, is that, right? So that when the middle is stretched, right? So that the one on the left and the one on the right are compressed, right? So, and then after some time, when these two particles are close together, then the middle one is compressed. Then you could imagine that the one on the right, left, and the one on the right are stretched, right? So the next one, is the so-called the symmetric mode. Okay. So what happens is that because you can see this 1 and 1, so that means that the x1 and x2 are always exactly doing the same thing. right? So they are doing the same oscillation. So that means that when this mass is moving to the right, the other mass is also exactly moving to the right at the exact same manner, right? But then after some time, right, so this one will go back to the left, and then this one will also go back to the left in the exact same manner. Okay. So, and then do it again and again. Okay, so then you can see that these two modes, okay, so which are called the normal mode, okay, and or oscillation mode, and they have different frequencies, right? So as we have solved already, right? So you can see that, well, in fact, one of them has a higher frequency than the other, right? So because of this k plus something, right? So this one, the oscillation more rapid than this one. So now let's try to understand, get some physical intuition on why this number and why this number. Okay. So yeah, let me go back to this slide before I and then I'll go back to the last slide. So the symmetric mode, right? So let me talk about this one first. The one that move together. Okay. So you can see that one thing that is interesting is that in this mode, the omega is still just square root k divided by m, right? So you may still remember that this is exactly just what happened for just one mass, one spring, the simple oscillator case. I have this square root k divided by m. Right? And it so happened that even when we have this coupled oscillators, as long as this is in the so-called symmetric mode, then the frequency, right, is still just this simple. So, and the way to understand it is that when it's doing the symmetric mode, right, so what's going on is that the two particles are moving at the exact same manner, right? So as I said, so then that means if you really look at what happened to the springs, what you realize is that, well, when it's moving to the right, this one is stretched, this one is compressed, but this one is still neither stretched or compressed, right? So after some time, when the mass is to the other side, right? So like this, then this one will be compressed. So this one will be stretched, but the middle spring, again, is neither stretched or compressed. That is to say, it seems that, right, so the spring in the middle is not playing any role at all time, right? So if you are in this symmetric mode. So therefore, if I look at it, it really doesn't matter whether you take this spring out or not, right? So if you are in the symmetric mode. Therefore, if I just take this spring out, I could just consider the following, right? So if I just take the middle spring away, and then what happened is something like this, right? So, and this one is stretched, this one compressed, right? Now, if the middle spring is out, that means that this whole system can be just considered as two independent oscillators like this, right? So then now you can see, right? So exactly, this one just act like this one mass, one spring, simple harmonic system, right? So, and the other also, right? So one mass, one spring, simple harmonic system. And that is why this is just exactly square root of k divided by m, right? So that's why. And of course, the other slightly different way to picture this is that you could, because of the fact that the middle spring is not playing any role, right? So that you could imagine that instead of just having a spring, I can just replace it with a massless rod, let's say, a rigid massless rod that cannot be stretched or compressed. So in that case, right, so I can consider the whole thing, this one as an entire box that has the mass 2m, right? Just a rigid body, mass 2m. That's equivalent to this system. And in that case, so what I'm considering is that I have this K over here, K over here. So I believe you also learned this system, right? So one mass, two springs on either side, right? So, and in that case, the oscillation frequency is just the total mass of the system, right? So divided by 2K, and this is, I'm sorry, the other way around. So 2K divided by the total mass of the system, 2m. That is again K divided by m. Right. So this is why this symmetric mode just acts like this one mass, one spring system over here. Okay, so now how about the anti-symmetric mode? So for the anti-symmetric modes, so all three springs are playing their role, right? So you cannot ignore any of them, right? So unlike the previous case. However, there is something that is still kind of not moving over time. That would be the exact middle part of this middle spring, right? So you could imagine that. So if you just put a marker at the middle part of the middle spring, over time, it's not moving anywhere, right? So that's not true for the other part, right? So if you put a marker over here, right, sometimes it's moving a little bit here, sometimes moving a little bit there. But if you put the marker exactly middle, not really moving. So because I'm assuming that the stretching is uniform. Okay. So and therefore, again, I can look at it in a different way. Okay, for the system is that imagine that you just kind of cut the system into half at this point. You cut it, right? So this is the fixed point, right? So if you cut it, and then you build two new walls, right? So for the two separate system, then what you have is something like this, right? So now on the left, I have a two spring system, right? So and then on the right, I also have the same two spring system. However, what happened is that the length of this spring is just half of the original length, right? So and then the length of this spring is also just the half of the original length. So now I told you last time, right? So is that if I cut the spring in half, the spring constant will be double, right? So originally the spring constant of this spring is K12, right? So if you cut it in half, you have the double of this, so 2K12. Right? So for this one mass two spring system, right? So then the frequency is K plus 2K12 divided by n. Okay. Right. Just looking at this, this is what you conclude. If you just look at this, this is also what you conclude. Right. And that is exactly equals to what we have just saw. Okay. Okay, so these are just kind of give you some intuition of how to think of these two numbers. Okay, so for the two frequencies. Okay, so next, let me introduce one thing which is known as the so-called normal coordinates. Okay, so this is nothing new here, no new skills here essentially, but this is just a definition of the so-called normal coordinate. So remember, if you just go back to look at the details of the process of solving this system of equations, right? So remember, the whole idea is about converting this system into another system which comes with a diagonal matrix. So that has been the idea the whole time, right? And then you know that with this transformation, I have do a variable change, right? So from this pair x1, x2 to this u1, u2. Right? So now this u1, u2, right? So will be another pair of numbers. So in this case, if I consider this two mass free spring system, you could explicitly calculate that this u1, u2, in fact, is this x1 minus x2 divided by 2, and this x1 plus x2 divided by 2, respectively, right? And this u1, u2, right? So what we did just now is that we need really this u1, u2 is just what appears in the middle of the process of the calculation, right? So and at the end, we never care about what u1, u2 are anyway. Okay, but here this u1, u2, okay, so it's what we call the normal coordinates of the system. Okay, so initially, so I will say that the x1 and x2 are the coordinates of the system. Okay, so this u1, u2 are called the normal coordinates of the system, and it's a linear combination of the original coordinates as you see here. So and now, if you treat this u1 and u2 as a new so-called new coordinate system, then in this coordinate system, right, so you will tell me that the equation of motion looks like this, right? So and what happens is that each of the you tell me that there are two independent oscillators here, right? So because I don't have any off diagonal terms here, right? So and then this u1 is just an oscillator oscillate at this omega-1 frequency, and then this u2 is just another oscillator oscillate at the other frequency omega-2, right? And it looks like, right, so they have nothing to do with each other, right? So there are no coupling between them. Okay. So again, right, so this is nothing new, but this is there's a name for this u1 and u2. Okay, so now let's try to solve an initial value problem. So that is to say, so now I know that the general solution is a linear combination of the two oscillation mode, right? So now we know that, and the question is, so then under what circumstances that we will have this mode, and under what circumstances we will have this mode? Okay, so or will they be there simultaneously or what? And that would depends on the initial conditions of the system. Okay, so before we go to the math, you could think about the following things, right? So is that if I have, again, if I have this system, right? So to start with, and let's say initially you try to pull both of the masses to one side by the same amount. Let's say that's what you do. That's the initial disturbance that you give to the system. Then what happened next? right? So you could probably visualize that what happened next is that they will both try to go back to the left, and then sometime later they will both try to go back to the right. Okay. So then that would be the case where you have only excite the symmetric mode. Okay. And the anti-symmetric mode won't appear at all. Okay. So on the other hand, again, imagine that now this time you're going to give this initial condition. That is, initially you pull the left mass to the left, pull the right mass to the right by the same distance. Then again, you could imagine that what happens is that they will keep doing this oscillation, this anti-symmetric oscillation. So, and of course, the more complicated question would be, what about initially? For example, I just move one of the mass to the left by some amount, but the other mass, I keep it fixed, so initially, and then I release my hand. Then what happened? So then this will be one example where both modes will appear. Okay. So let's try to see the mathematical methods. Right. So the general question is that given an initial condition, I'll use this word, right? So find out which modes will be excited. So this is, in general, the initial condition I give, right? So I pull this to the right by x1 naught, pull the other one to the right by x2 naught. Okay. And you could imagine that the initial condition can be even more complicated than that, right? So in addition to giving some initial displacement like what I have here, you could also give some initial velocity to the two masses. Right, so you are allowed to do that. But let keep things a bit simple. Right, so here I just imagine that you have some initial displacement, but the initial velocity of the two masses are 0. So first of all, right, so the general solution that we have derived is this one, right? Or you can write it as this one, right? So or write as the complex exponential form. Okay, so these three are all different way to express the general solution anyway. Okay, so let's say I'm going to just use, I will be going to, for convenience, I'm just going to use this one. Okay, this form over here. So now the initial conditions, right? So initial conditions as shown in the figure are given over here, right? So this x1 at time equals 0 is x1 naught. And this x2 at time equal to 0 is x2 naught. These two, okay. And then I assume that x1 dot, the initial velocity, the velocity of x1 at t equals 0 is 0. Right. So the other one, the inertial velocity is also 0. So what is the goal here? The goal is to find out these unknown constants. Right. So if you can find out these unknown constants, right, so you'll be able to tell me whether I have some oscillation for this mode or I have some oscillation for this mode. Right. So if you have this B1, B2 to be completely 0, so then I only have this mode. Right. So on the other hand, if I find that A1, A2 are completely 0, then I only have this mode over here. Right. So, or if you find that none of them are really 0, so then you know that you are in the superposition of the two modes. Okay. So then what we are going to do is to use these informations to figure out the numbers for this A1, A2, B1, B2. Okay. So again, let me write down the general solution first. General solution over here, and then I take derivative one time, right? So then this is the general solutions for the velocity of the two particles, like this, right? Just take derivative, so cosine becomes sine, sine becomes cosine, and with this extra factor omega 1 in front. So now I'm going to take the initial condition, right? So the initial condition, as I gave you in the last slide, right? So and then you just plug this thing into this first equation, and then plug this thing into the second equation over here. Then you find the relation between these constants with the initial condition. Okay. So from here, you'll find that this A1 is given by 1/2 x10 minus x20. Okay. And then this B1 is equal to this 1/2 x10 plus x20. Okay. And then for the A2, B2, okay, so you find that this A2 and B2 are both 0. So then that is to say, I just need to go to plug all this value, okay, back to my general solution expression. Then this is what I got. Okay, this A1 over here, this B1 over here. So you can see that, right? So if x1 naught is equal to x2 naught, that is, this term will go to 0. That means the whole first term will go to 0. Then I only have the second term, and the second term is the symmetric mode. And on the other hand, if I set this x1 naught is equal to minus x2 naught, then this term, the whole second term will go to 0. And only the first term survive, and that's why oscillation is in the anti-symmetric mode, right? So and that just verifies our intuition, right? So as I said initially, if you try to drag the two masses to the same side by the same amount, then it's symmetric mode, right? If you drag the two particles by the same amount but in opposite side, then you have anti-symmetric mode. But otherwise, right, so neither this one or this one would be 0, then you will get the linear combination of the two modes. Okay. So alternatively, just a slightly way to look at the problem, right, so is that I can just express everything in this so-called normal coordinates, as I said. In this case, right, so I've already mentioned is that this x1 and x2 is related by this u1 and u2 like this, right? So now you get this u1 and u2 governed by these two differential equations, right? And this in general, right? So this again, you can have this u1t is just I'm just copying the same thing one more time. Right, so the idea still would be finding out all these constants, right? So with this given initial condition, okay. So in this case, okay, because of the fact that I am giving you the initial condition in terms of the variable x1 and x2, right? So that's why, first of all, here you need to convert the number of x1, x2 initial condition in the initial condition for u1 and u2, right? And from u1, u2 at t0, and this u1 dot u2 dot equal to t0, and then you'll be able to find out the general solution for u1 and u2, right? So because from here you can see that this u1 at t equals 0 is exactly a1, and this u2 at t equals 0 is a2, and also this u1 dot at t equal to 0 is b1 omega, and u2 dot at t equal to 0 is b2 omega, right? So once you find out this, all this at t equals 0, you'll be able to find out these constants, and at the end you'll find out this u1 and u2 as a function of time. Okay, so this is a good time to stop here. So I have finished the entire main examples, okay, for this chapter, which is the free springs two mass system. Okay, so introduced the concept of this eigen frequency and normal mode. Okay. So next time we'll look at some other examples. Okay.